You know, lately it seems like everyone's buzzing about this whole next big thing in energy, fusion power, clean, limitless energy, right?
Right.
But let's be honest, for most of us, it feels kind of like, well, science fiction, right?
Yes, it can.
It all sounds amazing, but how do we actually get from this theoretical promise to a real world power plant that's actually, powering your home?
Absolutely. And that's where we're diving deep today into this.
Exactly. We're going deep on this one. And we have some really fantastic material to dig into, especially this paper from nuclear engineer, Dr. Lev Neymotin.
Yeah. Dr. Neymotin brings a really unique perspective. He's not just a theorist.
Right.
He's worked on fission reactors, but also on some pretty cutting-edge fusion stuff, particularly those tokamak cooling systems.
Oh, yeah, those are fascinating.
They use magnetohydrodynamics, which is basically using magnetic fields to manipulate the flow of liquid metal coolant.
Oh, wow. That's incredible.
It's like something out of a sci-fi movie, right?
It is.
But it's real, and it's happening right now.
Exactly. And I think the title of his paper, the original title, really kind of sets the tone for our deep dive today.
Yeah.
It was Fusion Reactor. Not so fast, if ever.
A little bit of skepticism there.
A healthy dose of skepticism.
Absolutely.
Which I think is great because there's a lot of hype around fusion.
There is.
So what we want to do today is cut through that hype with you.
Absolutely.
And really look at the core concepts of fusion power and the challenges of actually building a large-scale reactor.
Right. 1,000-megawatt reactor.
Exactly. The kind that could actually power a city.
The scale we need.
Right. Not just a lab experiment.
Yeah.
We want to get to the nuts and bolts, the crucial realities. So let's start with the fundamentals. What is fusion and how does it differ from fission, which is what we use in current nuclear power plants?
Okay, so fusion, that's what powers the sun.
Yeah.
And in a nutshell, it involves taking very light atoms, and we're talking specifically about isotopes of hydrogen.
Like deuterium and tritium.
Exactly. You smash them together at incredibly high speeds, and they fuse or combine into a heavier atom, helium.
And a whole lot of energy gets released.
A tremendous amount of energy.
Right.
In fact, each DT fusion reaction releases about 17.6 MeV.
MeV.
Mega electron volts, a unit of energy.
Okay.
Now contrast that with fission, which is what our current nuclear power plants use.
Right.
Fission takes heavy, unstable atoms like uranium, splits them apart.
Splits them.
Releases energy too, about 200 MeV per reaction.
Oh, wow. So actually more per reaction than fusion.
Yeah, a little bit more.
Interesting.
But here's the key difference. They're opposite processes.
Okay.
Fusion joins things together.
Right.
Fission breaks things apart.
Okay. And I guess with fusion, the real potential lies in the fact that you've got an abundance of these light elements like hydrogen, and you can, in theory, achieve a huge number of these reactions if you can control them.
Exactly. That's the big if.
Right.
But if we can master the conditions, the energy potential is enormous.
So that brings us to the conditions, right? Because the sun is this giant ball of superheated gas.
Right.
We can't exactly replicate that here on Earth.
Not quite, no.
So what kind of conditions do we need to create for fusion to occur here?
Extreme conditions.
Extreme how?
We're talking about temperatures over 100 million degrees Celsius.
That is mind-blowingly hot.
It's many times hotter than the core of the sun.
Wow.
That kind of heat is necessary to give the hydrogen nuclei enough energy to overcome their natural repulsion.
Repulsion.
They're both positively charged, so they want to push each other away.
Right, like magnets.
Exactly. So we need to overcome that, get them close enough for the strong nuclear force to take over and bind them together.
Okay, so 100 million degrees Celsius, and I'm guessing that's where those powerful magnetic fields come in.
Exactly. We use those in devices called tokamaks.
Right.
Essentially magnetic bottles
Yeah.
to contain the superheated plasma.
Because no material could withstand those temperatures.
Absolutely not.
Okay, so fusion. Very high temperatures, very strong magnetic fields. Fission, how does that compare?
Well, fission happens at much lower energies.
Okay.
The challenge with fission is actually controlling the chain reaction once it starts.
Right, preventing it from running away.
Exactly.
And that brings us to a really important safety point, which Dr. Neymotin highlights in his paper.
Yeah.
Fusion doesn't have that self-sustaining chain reaction.
Right.
If something goes wrong, if the conditions aren't maintained, the fusion reaction just stops.
It just kind of fizzles out.
Right. It's inherently safer in that regard than fission,
Much safer.
where you need those elaborate fail-safe systems.
Right, to prevent a meltdown.
Exactly.
So fusion has that inherent safety advantage.
Okay, so we've got the basics. Fusion joins light atoms, releases energy, requires these crazy high temperatures, powerful magnetic fields, and doesn't have this runaway reaction risk.
Yeah.
But let's get to the real challenge.
Right.
Actually building a power plant.
Right.
A 1,000 megawatt reactor.
Yeah.
That's where things get really complicated.
Absolutely. Dr. Neymotin outlines several key challenges.
Okay.
And the first one is sustaining a stable fusion plasma.
Okay, so you've got this incredibly hot plasma.
Right.
It's confined by magnetic fields.
Yeah.
But how do you keep it stable over time?
Well, imagine trying to hold something as hot as the sun in a magnetic bottle that's about the size of a small house.
That's a pretty wild image.
And it's not easy to keep that plasma behaving itself.
Right.
The rate at which fusion reactions happen is very sensitive to even tiny changes in temperature and fuel concentration.
So if it fluctuates a little bit,
Yeah.
the reaction rate
Changes dramatically.
and that's a problem.
Absolutely. Keeping the conditions uniform across that entire volume, it's a huge challenge.
It's not just about achieving fusion.
Yeah.
It's about maintaining it.
Exactly. Sustaining it.
Okay, so keeping things stable is a challenge.
Right.
What else?
Well, then there's the issue of plasma instabilities.
Okay, what are those?
Imagine the plasma. It's not perfectly smooth.
Right.
It can develop waves, eddies.
Kind of like turbulence.
Yeah, like turbulence.
In this super hot soup.
Exactly.
Okay.
And sometimes even violent disruptions.
What does that mean, a disruption?
Well, it means the plasma can essentially slam into the reactor walls,
Oh, wow.
causing damage.
And obviously you don't want that.
No, definitely
Yeah.
not. These instabilities can stop the fusion reaction.
And they can also damage the reactor itself.
Exactly.
Okay, so that's a big problem.
It's a significant hurdle.
So, challenge number 1, keeping this incredibly hot, unstable plasma stable.
And continuous.
Right, because right now, fusion experiments, they run in these short bursts, right?
Yeah, seconds or minutes.
But a power plant would need to run continuously for months, maybe years.
Years, ideally,
Right.
for it to be truly practical.
Okay, so challenge number 1, stability and continuous operation.
Right.
What's the next big hurdle?
The next one is managing the fuel.
Okay, so we're talking about getting the fuel in and getting the byproducts out.
Exactly. In a 1,000 mW fusion reactor, you'd have something like 10 to the power of 18 fusion reactions happening every single second.
That's a crazy
It's
number.
an astronomical number.
Right.
And yet, that only consumes about 0.7 kilograms of fuel per day.
Wow. So even with all those reactions, it's a relatively small amount of fuel.
Relatively small.
But there's a catch, right?
There's a catch. Not all the fuel that's injected actually undergoes fusion.
Not perfectly efficient.
No. This is what's called a low burnup fraction.
Okay.
So the reactor needs to process a much larger amount annually, something like 250 kilograms.
So for every tiny bit that fuses, a lot more has to be cycled through.
Exactly.
So it's a constant flow.
It is. You're constantly feeding it and dealing with the exhaust.
Okay, and that exhaust is what, helium?
Primarily helium, yes.
So we've got the fuel going in, the helium ash coming out.
Right. And the fuel needs to be delivered very precisely to maintain that uniform plasma we talked about.
Right, to keep things stable.
Exactly.
Okay, so fuel management, another big challenge.
It is.
And then there's those massive magnets.
The superconducting electromagnets, yes.
Which Dr. Neymotin talks about.
They're essential for a fusion power plant.
But they have their own set of challenges, right?
They do.
Like, they need to be incredibly cold.
Incredibly cold. We're talking about temperatures near absolute zero.
Wow.
Around 4 Kelvin, which is minus 269 degrees Celsius.
So you've got the hottest thing in the universe, the plasma, and right next to it, you've got these magnets that are almost the coldest things in the universe.
Pretty much, yeah. And that creates enormous engineering challenges.
Just managing those temperature differences.
Exactly. Maintaining the cryogenic systems.
And then on top of that, you need a super reliable power supply.
Oh yeah, that's critical. If there's even a brief power outage, the magnetic field could collapse.
And that would be bad.
Very bad. The plasma would slam into the reactor walls.
And cause a lot of damage.
Potentially a catastrophic event.
Okay, so reliable power is essential.
Absolutely.
And then there's the energy it takes to run all the systems.
Right.
The cooling, the vacuum pumps, the initial heating of the plasma.
All that overhead power consumption.
It eats into the efficiency, right?
It does.
So you have to generate more power just to keep the whole thing running.
Exactly.
Okay, and then there's the heat from the neutrons
Right.
that bombard the reactor walls.
They carry a lot of energy.
And you have to manage that heat somehow.
We need efficient cooling systems.
And then the neutrons themselves cause damage to the materials.
They do, more so than in fission reactors.
So you have to replace components periodically.
Yeah, using remote handling systems.
It's a pretty hostile environment inside a fusion reactor.
It is.
Okay, so we've talked about the plasma, the fuel, the magnets, all these challenges.
Yeah.
But there's one more we need to talk about, and Dr. Neymotin calls it a central challenge.
Tritium.
Right, the tritium fuel supply.
It's a big one.
So, first of all, what is tritium?
It's a radioactive isotope of hydrogen,
Okay.
and it has relatively short half-life, about 12.3 years.
Meaning it decays relatively quickly.
Fairly quickly, yes.
Okay.
And is incredibly rare in nature.
So how rare are we talking?
The entire world inventory is estimated to be only around 20 kilograms.
Wow.
That's a tiny amount.
That's not going to power a whole lot.
No, not at all.
So how much tritium would a 1,000 milliW fusion reactor need?
Somewhere between 50 to 100 kilograms per year.
So we're way short.
Significantly short.
So where do we get the tritium?
We have to breed it.
Breed it?
Yeah, inside the reactor.
How does that work?
We use the neutrons produced in the fusion reaction to bombard lithium.
Lithium.
Yeah.
And that creates tritium.
It can. It's a nuclear reaction.
Okay.
But it's tricky. We need to achieve a breeding ratio greater than 1.
Meaning you produce more tritium than you consume.
Exactly.
But that's hard to do, right?
It is. Some neutrons are always lost.
Okay, so if we can't breed enough tritium, fusion is a non-starter.
It's a non-starter.
Okay. And then there's the fact that it's radioactive.
Right.
And hydrogen, which is notoriously difficult to contain.
It is. Tritium can easily disperse. It can also form tritiated water.
So there are safety concerns.
Absolutely. We need very careful handling procedures.
So a rare radioactive gas that we need to create inside the reactor, which requires special handling. The tritium fuel cycle is a huge challenge.
It is.
Dr. Neymotin actually lays out a very helpful comparison between a 1,000 milliW fusion reactor and a similarly sized fission reactor.
Yeah, he does.
It highlights the key differences.
Absolutely.
So let's go through some of those key differences. First, the fuel itself.
For fusion, it's deuterium and tritium, with an annual usage of around 250 kilograms.
Okay.
Fission uses enriched uranium, about 27,000 kilograms per year.
Wow, that's a huge difference.
It is.
What about the on-site fuel inventory?
Well, in a fusion reactor, you only have a few grams of DT in the plasma at any given time.
Okay.
And maybe a few kilograms of tritium in storage.
Right.
A fission reactor has about 75 tons of uranium in its core.
Per 5.
75 tons.
That's a lot of fuel.
It is.
Yeah.
And it can last for years.
Okay, so fusion is very lean in terms of on-site fuel.
Very lean.
But it requires that constant feed.
Continuous flow.
Right. What about the fuel handling?
Well, fusion requires continuous injection of fuel and removal of the helium ash.
It's a more complex process.
Much more complex. Fission, they refuel in batches every year and a half or so.
Okay.
The fuel rods just sit there doing their thing.
So fusion is like a living, breathing thing?
You could say that, yeah.
Fission is more like set it and forget it.
Kind of, yeah.
For a while, at least.
Right.
Okay, what about waste products? That's a big concern for people.
Rightfully so.
When it comes to nuclear power.
Yeah. Well, fusion's primary waste product is helium gas, which is harmless.
Okay.
There will also be some neutron-activated materials, but those are considered intermediate level waste.
Okay.
And there's the possibility of some tritium leakage, which is radioactive.
Right.
Fission, of course, produces high-level spent nuclear fuel.
Which is a big problem.
It is. It requires long-term storage.
Okay, so fusion has a clear advantage there.
It does.
In terms of waste.
Yes.
Okay, let's talk about reaction stability.
Okay.
Because that ties into safety as well.
Right.
So fusion, not self-sustaining.
Correct.
You need constant control.
Constant control.
If something goes wrong, the reaction just stops.
Plasma quenches.
Right. No meltdown risk.
No meltdown risk.
Fission, on the other hand, it relies on that self-sustaining chain reaction.
Right.
Which can be stable if it's controlled.
Right.
But if it's not, you could have a runaway reaction.
Leading to a meltdown.
Exactly.
So both technologies have their own safety considerations.
So, looking ahead, based on Dr. Neymotin's analysis, what are the biggest remaining challenges for fusion?
He highlights several, and they're all pretty significant.
Okay.
First, tritium self-sufficiency.
Right. If we can't breed enough tritium, it's a deal breaker.
It's a deal breaker.
What else?
Plasma stability and control.
Right.
We need to demonstrate continuous operation for years without major disruptions.
And we haven't done that yet.
Not yet.
Okay. What?
Materials durability.
Right, because those neutrons are constantly bombarding the reactor walls.
They are.
And causing damage.
Damage that could necessitate frequent replacements.
Okay.
And that would make fusion very expensive.
Right.
And then there's the overall complexity and cost of the entire system.
Right. Integrating all these
Not
subsystems.
they all work together seamlessly.
Affordably.
Affordably, yeah.
Okay, those are some pretty big challenges.
They are?
Dr. Neymotin also briefly mentions alternative fusion fuels.
He does. Fuels like deuterium, or proton-boron 11.
Okay. What's the advantage of those?
Well, they could potentially eliminate the need for tritium breeding.
Oh, that would be huge.
It would.
And reduce the amount of radioactive waste. But there's a catch, right?
There's always a catch.
What is it?
These reactions require even higher ignition temperatures
Than DT fusion.
So
So even harder to achieve.
much harder.
So those are more long-term research projects.
They are.
So bringing it all together, what's Dr. Neymotin's overall perspective on the future of fusion power?
I'd say he's cautiously optimistic.
Okay.
He acknowledges the progress we've made.
Right.
He believes we can achieve ignition,
Okay.
develop solutions for the magnets, the cooling, all of that.
Right.
But he's also realistic about the challenges,
Okay.
especially tritium breeding and materials durability.
Right. Those are big unknowns.
They are.
And ultimately, he says the deciding factor will be economic viability.
Absolutely.
If it's too expensive, no one's going to build it.
Exactly. It has to be competitive with other energy sources.
And that brings us back to the title of his paper, Fusion Reactor, Not So Fast, If Ever.
Yeah, a dose of reality.
The dose of reality.
Fusion is incredibly promising, but it's not a sure thing.
He even says that fusion remains the energy source of the future and always will be.
A classic quote.
It is.
But there's some truth to it, you know.
Right.
We've been pursuing fusion for decades.
And we're still not there yet.
Not yet.
So that was a pretty deep dive into the world of fusion power.
It was.
We've seen the incredible potential, but also the immense challenges.
The challenges are real.
And the key takeaway is it's not just about solving individual technical problems.
No.
It's about integrating all those solutions into a system that is reliable, safe, and affordable.
And sustainable.
And sustainable, right. So it makes you think, given all these hurdles, what's going to take to make fusion a reality?
What's the tipping point?
Right. Will it be a technological breakthrough?
Maybe a new material that can withstand those neutron bombardments.
Or a more efficient way to breed tritium?
Possibly.
Or maybe it will be a shift in priorities.
A greater sense of urgency around climate change, perhaps.
Right, which could lead to increased funding and research.
Exactly.
So is fusion destined to always remain just over the horizon?
It's hard to say.
Or will we see it become a practical energy source in our lifetime?
Time will tell.
It's something to think about as we navigate this complex energy future.
Absolutely.
Well, that's all the time we have for today.
Thanks for having me.
It was great to have you on the show.
It was a great discussion.
And thanks to you, the listener, for joining us for this deep dive.
We hope you found it insightful.
And we'll see you next time.
See you next time.